Hey, I want to look at multicollinearity, and this is Multicollinearity 101 and how it affects marketing mix modeling. Because multicollinearity can be that silent killer of attribution because correlation can kill attribution. So let's look at what all that means and what is multicollinearity in the first place. Now, in this guide, this is a very simple guide. I do have another advanced guide which I'll make another video on, and this goes into a lot more detail on running some actual data like detecting multicollinearity, VIF, visualizing the problems, running a bootstrap analysis, and so on. But for this MMM 101 or multicollinearity 101, let's stick to the basics and then just get a very high level overview of what the problem actually is. So we usually see this when there are marketing channels that move together. And when I say move together, they have very similar spend patterns. So, for example, let's take a product launch or a festival season or like a Black Friday holiday. So, when you're expecting more sales, you'd probably increase spend not just on one channel but across channels. Let's say we're approaching Black Friday and we spend more on TV and radio, and that spend increase is very correlated. So that is the big problem. Now we just put this into our media mix modeling, and you'll find out that sometimes the ROI is negative, or even slight changes in data can really flip the model upside down. So if you notice all these problems, then that's because the TV and radio is really highly correlated to each other, and that is the big problem. And we need to solve this. So you already heard me speak about this term correlation. So here we have a simple math where we see that TV and radio is not that highly correlated. 0.3 is not highly correlated, which is actually good for our marketing mix modeling. Whereas if you see Facebook and Instagram, for example, if we are spending evenly across them, then there's really high correlation, close to one, and that is a problem. So again, here, the lower correlation is the better, and the higher you go, that's the problem. We don't want to stay in that. So here I have some examples. So we have TV and radio over here, and you see they're really close in this time series graph, even though they're not overlapping each other. And correlation doesn't mean they have to overlap. It can just be, hey, TV spend is 1.5 times of radio spend, and that is enough to flip the results for marketing mix modeling. So here TV and radio are highly correlated. Just visualizing it, just looking at this graph, you can tell they are correlated. Like if I turn on TV and search here, you'll see there's no correlation. Maybe during the peak Black Friday season there is, but you see here there's not much correlation over there. So in situations like this where they're high correlated, the model cannot really tell what is driving the sales. So if it is TV or radio that's driving sales, because it's very similar. So if you just run this data as it is, you'll see with the regression, you'll maybe see TV gets $5 credit or $5 ROI, and radio gets nothing, minus $2. And this makes no sense. And here we have this issue of negative ROI. So through this video, we'll look at some simple solutions, some advanced solutions as well. And once you run through that, you'd probably get TV 2.5 credit and radio 1.8 credit and so on, which is quite positive and reasonable. Now, why do we want something like this and not this? Of course, this negative ROI doesn't make sense in the first place. But also, if you're running budget analysis or planning your scenario of how you're going to spend in the next 3 months, using this ROI over here, negative ROI, it's going to be just random budget allocations that you would get, which you can't really action on, and the business is heavily impacted. So you really need something like this if you're going after budget optimization and scenario planning and so on. So some reasons of why could this even happen? So like I spoke about holiday seasons, all channel increase for Black Friday, Cyber Monday, and the correlation is really high, 90% plus. If there are product launches, then you have all these activities like PR, digital TV, and so some of them might get pushed down. Let's say TV and digital get credit and PR gets pushed completely out, which doesn't make sense. And a few other examples here. So some of the big problems, again, wrong attribution where TV gets all the credit and then Facebook gets nothing. Unstable results. Like if you just add one extra data point, then the model completely flips the ROI, which is again a bad signal over here. And this is heavily impacted on the business, right? Bad decisions. So it says cut Facebook, invest in other channels, and you do that and you realize that was a bad decision because now you can't go back, and that leads to wasted budget. So how do we solve this? Now we've understood the problem. Let's try and understand what kind of solutions are there. So the quick check, like what we just did, look at the graphs, look at what kind of patterns you can identify there and see if there are correlation that you can figure out, which is very obvious by looking at it. But other than that, you can look at correlation. You can run a simple correlation matrix on all the channels, and then you'll get the matrix like this. Less than 0.7 is good. Actually, I would probably go even as far as zero point 0.6 or zero point 0.5, which is good. And then warning 0.7 to 0.85. Anything above this is really bad. And we have something called as the VIF score, which is variance inflation factor. And this actually measures the multicollinearity. So if you're looking at these two things and then you see that the value is over less than 5 over here, then it is good. Now 5 to 10 is bad and greater than 10 is good. So you have to look at these two next to each other, I would say, because sometimes you'll see that channels are not correlated enough. But then if you look at the VIF score, then you might get a high VIF score, which means it's bad. So look out for both of these numbers and see what makes sense. Now let's get to the solution. So we've identified that we have problem either by looking at the charts themselves or looking at these numbers over here, correlation or VIF score. So now comes the simpler solutions. Again, this is not one size fits all. There are various levels to this. So you can easily go and remove the similar channels, right? So you saw Facebook and Instagram had 0.95 high correlation, then just remove Instagram. So this is a simple and immediate fix, but I mean, you can think of the cons. We lose information about Instagram now. So if you still want to use that, you can combine them into groups. So you can just say social media where Facebook, Instagram, TikTok all get bundled up together into one channel. This could give you better results, but again, the con is it's less granular now because instead of looking at each channel, you're looking at like a category. The other thing might be you could run tests like A/B test or incrementality test, like turning TV off in half of your market for entire 4 weeks and know the actual incremental impact of TV. But this again requires testing more sales that gets lost, or there's a huge opportunity cost here. And then the other one is you just go forward looking and then stagger some of your campaigns going forward so that you launch maybe TV a week and the third week you launch digital and then maybe email week 5 so that they're not getting similar spend and there is some natural variance that can be created. But then this is not optimal for all businesses because if you have past 2 years worth of data, you can't really action on it. Okay, some of the advanced solutions, again, you might have seen, I'm not going through the math. This is purely just to get a high level overview. Like I showed initially in the part 2, I'll go through all the details. So in regularization, so here is one approach where we share credits across all the channels. And even here, there are multiple variations, but the simple example is instead of giving all the credit to just one channel, regularization forces the model to share credit between each other. So without regularization, you might see something like this. TV gets 10, radio gets -2 now. Whereas if you put regularization in here, TV might get 4, radio might get 3, and then print might get 1. So these are all fair share. That's fine. And we have few techniques here. There is obviously L2 regularization, where you can think of this as shrinks all coefficients towards each other, similar to what we saw here. So you can see there's not much variance here, like they're close to each other. And there is another L1 regularization where you can expect some of the channels to go to 0. So for example, if you had 15 channels with confusing coefficients, you can run L1 regularization and then you end up with 6 main channels and others are all set to 0, which you can just directly ignore and you just go after the top 6 channels. Or if you want best of both worlds, you can go for an elastic net, which combines ridge and lasso regularization. So it also shares credits, but also removes redundant channels. So this is like the best of both worlds. And if you don't know which one to pick, you just go with this first and then iterate over the other techniques. And even advanced or even nicer approach would be residualization, but then this requires a few prerequisites. So think of this like peeling an onion, right? So you have, let's say, a funnel where you have the top awareness and then at the bottom you have all the sales. So if you have something like this, which is very hierarchical, then going for residualization makes sense. So this is like peeling an onion. You analyze one channel first, remove its effect, then analyze what's left. So like I said, when do we use this? We use this when there's clear hierarchy, where there is general awareness channel at the top, then there is the consideration funnel step, and then the conversion funnel over here. And this order matters a lot. And we start with the top, we analyze the broader channels first and then go deeper and then deeper. So a quick comparison guide over here where you can read through all this and just summarizes what we just spoke about. Some real world examples. So we can see Black Friday can cause multicollinearity because all the channels might get spike of hundreds of percentage points. If you take an example of a beverage brand and you see TV and YouTube ads had 0.92 correlation, you can go for a solution like residualization, analyze the TV first, then YouTube on the remainder. So here's a way to think of this like a decision tree. So if your correlation is greater than zero point 0.9, then yeah, try ridge first, then remove if needed. If you have 10 plus channels, then use elastic net or lasso, because as we saw, some of the channels coefficient can go to zero, and instead of 10 plus channels, you might be left with 5 or 6. And if you have clear hierarchy, then go for residualization. So I hope that wasn't too complicated and you get a high level overview of this. And again, comment down if you want this guide, I'll send it over. But the idea is we need to be careful of how we choose the data points and the columns of data that go into our marketing mix modeling, especially if we know about multicollinearity, and you can question your practitioners or data scientists on team or vendors or consultant, whoever you engage with, how we deal with this. And if you're able to run some pre-analysis before giving this data to them, or ask them, can they do that for you and then give it back to you. Either way, we need to figure this one out because it has real business implication. Until next time, see you.